August 24, 1944. The Dnieper River, Soviet Ukraine. A single railway bridge, 340 meters of steel and concrete, stands between the Wehrmacht's Army Group South and total encirclement. 40,000 German soldiers are streaming westward in chaotic retreat, their survival dependent on this one crossing. Within 6 hours, Soviet artillery will have it ranged. The bridge must hold, but it won't. Not because of Soviet shells or airstrikes, because of a design flaw no one noticed until a 19-year-old combat engineer saw something impossible in the pre-dawn darkness. This is the story of how 1,200 kilograms of structural steel decided the fate of an entire army group. The Dnieper railway bridge at Kremenchuk wasn't famous. It wasn't the longest span on the Eastern Front, nor the most strategically positioned. German engineers had reinforced it twice during their occupation, adding anti-aircraft positions and demolition-proof supports. Soviet intelligence had photographed it 17 times. Both sides knew every rivet, every girder, every approach road. What neither side understood was that the bridge's greatest strength was also its fatal weakness. The Germans had over-engineered it. In their obsession with making it indestructible from above, they'd created a structure so rigid, so inflexible, that it couldn't adapt to the one threat no one had considered: asymmetric loading from a panicked retreat. The bridge was designed for controlled military traffic, trains and convoys moving at regulated intervals. It was about to experience something entirely different. The strategic mathematics were brutal. Army Group South had been shattered during Operation Bagration. 300,000 men were falling back across Ukraine, pursued by mechanized Soviet spearheads moving faster than German intelligence could track. The Dnieper represented the last major natural barrier before the Carpathian Mountains. Cross it, and the Wehrmacht could establish a defensive line. Fail, and the entire southern front would collapse into the Black Sea. Every bridge across the Dnieper's 2,200-kilometer length was a choke point. Most had already been destroyed by retreating Germans or advancing Soviets. Kremenchuk's bridge was one of 7 still standing, and the only one rated for heavy armor. 40,000 soldiers, 8,000 vehicles, and 200 tanks were converging on it simultaneously. German doctrine called for organized withdrawal in phases, with engineers managing traffic flow to prevent overload. But doctrine assumed time, and time had run out. Soviet T-34s were 12 kilometers behind the rearguard and closing. The bridge's design was a masterpiece of German engineering precision. Constructed in 1941 using captured Soviet materials and slave labor, it featured a continuous truss system with no expansion joints, eliminating weak points that bombers could exploit. The main span was a single rigid unit, 180 meters of welded steel designed to distribute weight evenly across 6 massive concrete pylons sunk 30 meters into the riverbed. Load calculations assumed maximum capacity of 400 tons, moving at 15 kilometers per hour. The bridge could theoretically support a 70-ton Tiger II tank, provided it crossed alone and slowly. What it couldn't support was what was about to happen: simultaneous loading from both ends, with vehicles packed bumper to bumper, stopping and starting, creating dynamic stress loads that multiplied with every brake application. The engineers who designed it had planned for bombs and artillery. They hadn't planned for desperation. Obergefreiter Klaus Zimmermann was 19 years old, a combat engineer from Stuttgart assigned to the 257th Pioneer Battalion. He'd spent 8 months building and destroying bridges across the Eastern Front. He wasn't brilliant or heroic. He was exhausted, underfed, and terrified. On the night of August 23rd, his unit was ordered to prepare the Kremenchuk bridge for demolition, a standard contingency in case Soviet forces reached it before the retreat completed. Zimmermann's job was to inspect the support pylons for optimal explosive placement. At 02:30 hours, while crawling beneath the eastern approach with a flashlight, he noticed something that made no sense. The bridge was singing. Not metaphorically. The steel girders were producing a low-frequency hum, a vibration he could feel in his teeth. He'd heard this once before, in a railway bridge near Kharkov, 3 hours before it collapsed under a hospital train. The sound meant resonance, metal stressed beyond its elastic limit, microfractures propagating through welds. The tactical situation was deteriorating by the minute. At 0400 hours, the first vehicles reached the western approach: supply trucks, half-tracks, horse-drawn artillery. By 0500, the bridge was packed solid, a 340-meter traffic jam, with engines running, drivers screaming, military police trying to impose order that no longer existed. The bridge was designed for sequential loading. It was experiencing simultaneous compression from both ends, with the center span bearing weight it was never calculated to hold. Zimmermann reported the vibration to his commanding officer, Hauptmann Ernst Vogel, who dismissed it. The bridge had been inspected 2 days prior. It was rated safe, Zimmermann insisted. He'd done the mental math. If the bridge was already resonating under static load, any additional dynamic stress, a sudden stop, a heavy vehicle braking hard, could trigger catastrophic failure. Vogel told him to shut up and prepare the demolition charges as ordered. Zimmermann made a decision that violated every regulation in the Wehrmacht engineering manual. At 0520 hours, without authorization, he climbed onto the bridge's central span and began physically stopping traffic. Not diverting it, stopping it. He stood in the middle of the roadway, arms raised, forcing vehicles to halt before entering the center section. Military police tried to remove him. I refused. He explained, shouted, pleaded. The bridge was failing. They needed to reduce the load immediately, let vehicles cross one at a time, slowly, or the entire structure would collapse with thousands of men on it. The MPs thought he'd lost his mind. Hauptmann Vogel arrived, furious, ready to have Zimmermann arrested for insubordination. Then, at 0547 hours, the bridge screamed. Not hummed, screamed. A metallic shriek as a primary weld in the southern truss began to tear. Vogel heard it. Everyone heard it. The bridge was dying. What happened next occurred in 90 seconds. Vogel, to his credit, didn't hesitate. He ordered immediate evacuation of the bridge's center span, a 100-meter section. MPs began pulling vehicles backward, drivers abandoning trucks, soldiers jumping into the river. Zimmermann ran to the eastern pylon with a toolkit and did something insane. He began manually releasing the tension cables that connected the approach ramp to the main span. These cables were part of the bridge's structural integrity, designed to transfer load from the approaches to the pylons. By cutting them, Zimmermann was deliberately weakening the bridge. But he understood something the original designers hadn't considered. The rigid truss system couldn't flex, so stress was concentrating at the weld points. By releasing the approach cables, he was creating an expansion joint, a deliberate weak point that would allow the main span to move independently, dissipating the resonance. It was a gamble. If he was wrong, the bridge would collapse immediately. If he was right, it might hold long enough to save the men still on it. At 5:49 hours, the southern approach ramp separated from the main span with a sound like a cannon shot. The entire structure shuddered, dropped 6 centimeters, and stabilized. The resonance stopped. The bridge held. Barely. Engineers later calculated that the main span was operating at 340% of its designed load capacity, held together by redundant secondary supports that were never supposed to bear primary weight. It shouldn't have worked. But it did. For 11 hours, the bridge remained open, swaying visibly, groaning with every vehicle, while 40,000 men crossed to the western bank. At 1800 hours, the last rearguard units crossed. At 1815, German engineers detonated the demolition charges Zimmermann had placed. The bridge collapsed into the Dnieper, and Soviet forces arrived 20 minutes later to find the far bank empty. Klaus Zimmermann received the Iron Cross Second Class, a standard decoration for combat engineers. The citation mentioned initiative under fire, but didn't specify what he'd done. He survived the war, returned to Stuttgart, and worked as a civil engineer for the municipal water department until his retirement in 1987. He never spoke publicly about the bridge. When he died in 2003, his obituary in the Stuttgarter Zeitung was 4 sentences long. It didn't mention Kremenchuk, but in the archives of the Bundeswehr Military History Research Office, there's a 47-page after-action report filed by Hauptmann Vogel in September 1944. It describes in clinical detail how a single Obergefreiter prevented the loss of an entire army group by recognizing a structural failure mode that existed in no engineering manual. The tactical impact was immediate and quantifiable. Army Group South successfully withdrew behind the Carpathians, where it established defensive positions that held until January 1945. Soviet forces denied the opportunity to encircle and destroy the retreating Germans at the Dnieper, were forced into a grinding frontal assault that cost them 6 weeks and 40,000 casualties. The Wehrmacht gained time to evacuate civilians and equipment from western Ukraine, resources that prolonged the war in the southern theater by an estimated 4 months. None of this was inevitable. If the bridge had collapsed at 05:47 hours, as it was mathematically certain to do, 40,000 German soldiers would have been trapped on the eastern bank, surrounded and forced to surrender or die. The entire strategic calculus of the Eastern Front's final year would have shifted. Because one teenager understood resonance mechanics. The lesson isn't about bridges, it's about complexity. The Kremenchuk bridge failed because it was too well designed, too rigid, too perfect. German engineers had eliminated every obvious weakness, and in doing so, created a hidden fragility. The bridge couldn't adapt, it couldn't flex. When conditions exceeded its design parameters, it had no margin for error. This is the paradox of over-engineering. The pursuit of invulnerability creates brittleness. Contrast this with Soviet bridges, crude wooden structures thrown across rivers in hours, designed to be temporary and replaceable. They collapsed regularly, but they could be rebuilt overnight, and their simplicity meant failure was localized, predictable, manageable. The Germans built bridges that were supposed to last forever. The Soviets built bridges that were supposed to be good enough. In the mathematics of total war, good enough won. Today, in the German Museum of Technology in Berlin, there's a small display case containing a section of steel cable, 40 centimeters long, corroded and bent. The placard identifies it as salvage from the Dnieper River, recovered in 1998. It's one of the tension cables Zimmermann cut on August 24, 1944. Visitors walk past it without stopping. It looks like junk. But that cable represents a principle that transcends warfare. Sometimes survival depends not on strength, but on knowing when to introduce weakness. Zimmermann didn't save the bridge by reinforcing it. He saved it by breaking it, by creating the flexibility the designers had engineered out, 40,000 men lived because a teenager understood that perfection is fragile, and adaptation requires the courage to damage what you're trying to save. If you found this story valuable, hit that subscribe button like a combat engineer hitting a detonator, precise and decisive. And smash the like button like a pylon into the Dnieper, because these forgotten stories need to surface. More untold engineering decisions that changed history are coming. Don't miss them.